All right, so today we're talking about higher order polynomials. So we're going to start with the kind of the graphs of y equals x to the 2, x to the 3, x to the 4, x to the 5, and then we're going to look at some other graphs and just kind of the general behavior of these things. All right, we know what the graph of y equals x squared looks like. It's a parabola. Y equals x to the third. You could pull out a graphing calculator, but in the interest of time, I'm just going to kind of show you what it looks like. Actually, it might be better if I move this axis up here. Okay, y equals x to the third. Okay, if we take a negative number to the third power, it's going to be negative and it's going to be larger. But if we take a positive number to the third power, it will be positive larger. So that's going to be the shape of it. X to the fourth. Okay, x to the fourth looks pretty similar to y equals x to the 2. Except, okay, well, when you take a number bigger than 1 to the fourth power, it's going to be larger than if you had just squared it. And if you take a number less than 1 to the fourth power, it's going to be actually closer to 0 than it would be if you squared it. Think about what happens when you square a number less than 1. It actually gets smaller. So in thinking about that, it's going to be steeper, and then it's going to kind of be flatter in the middle. But that is not super important for our purposes here. And then x to the 5, you could kind of have the same reasoning as x to the 4, except, it's going to has an odd degree, so it's going to, again, be steeper and also flatter in the middle. That was not a very good graph, but did a good job. And then, it looks like we have x to the 6. I don't think I did that one yesterday. Okay, x to the 6, even steeper than x to the 4th on the outsides and even flatter, but, almost. And there's not a sharp corner there. But almost imperceptibly different from. Okay, now, with these, this is going to look a little different. Okay, we already know what this looks like. We graphed second-degree polynomials in the fall, and, if y equals x minus 1 multiplied by x minus 2, y is equal to 0 when x is equal to 1 or x is equal to 2. So we know that, it has these points on it. We also know that it's a parabola that opens upwards because it's positive x squared. So it's going to look something like this. And that's going to be a decent sketch. With this one on the right, we probably need, a little more analysis. Okay, so, just for the purposes of demonstration, I've brought up a graphing calculator, and I've entered y equals x times x minus 1 times x, it should be minus 2. Let's see if I can change that. Yeah, that'll help. And then I'm going to change the window to be like, I definitely need to go from -2 up to 4 or 5. And probably -5 to 5. Okay, and so we see it kind of went up, it turned back, and then turned around and went up again. Okay, so it's kind of got the same outsides as y equals x to the third. It goes down to the left and up to the right. But in the middle, it's got, some intrigue. So I'm going to just give a little sketch of it over here. Okay, and it looks, it came from below. Intercepted at 0. Went up, it came back down, and then it went back up. So that's about what we got. And then the question is, well, what would happen if we added an x minus 3? Well, if I have 4 powers of x here, I know it's going to be a 4th degree polynomial. So it should look kind of like x to the 4th, but maybe it's got some interesting stuff happening in the middle. So I'm going to go back into y equals. Then I'm going to just add in this last factor. Or maybe I'll just insert it in the front. X minus 3. Close off that parenthesis. Okay, and then we see, it looks the same on the outside. It's got these arms that are both going up. But in the middle, we've got some excitement happening. And it kind of looks like a W, so I can draw that. Maybe I'll just adjust where 3 is. Perfect. And for our purposes, this is a perfectly good sketch. Okay. Kind of the vertical scale, not that important. Really, the shape of the graph, the direction of the arrows, and the intercepts are what we're really looking for when we ask you to sketch a graph. All right, and then it asks, well, what if we put a negative in front of all of these expressions? Well, really what we would be doing is we would be taking y, and we would now have negative y. And if it was negative y, it would become positive y. So, okay, this point here, this bottom vertex is kind of going to go up here. And then the arms, instead of going up, will go down. And so, probably in Algebra 2, you would have called that, a reflection across the x-axis. I would just say it's upside down. So again, I'm just going to kind of turn this thing upside down. And then instead of a W, it becomes an M or something. Y goes to negative y. Graph is turned upside down. Or reflect across the x-axis. Okay, the end behavior of polynomials. And that's basically what's happening on the outsides. Where are the arrows pointing? What's really happening with this function as x gets really large or really negative? Okay, so really what this depends on is the degree and the leading coefficient. Okay, so if we have an even degree, versus an odd degree, then we'll have, different end behaviors. And then the sign of the leading coefficient being positive or negative will pretty much determine what the end behavior of our polynomial is. But the good news is you really only have to remember y equals x squared and y equals x. If you know what those look like, then you can figure out the end behavior of any polynomial. So we're thinking, okay, an even degreed polynomial with a positive leading coefficient would be something like y equals x squared. And we know what the graph of that thing looks like. It's a parabola that opens up. And so we saw that when you said that fourth degree polynomial that looked like a W, okay, it had some weird stuff happening in the middle, but on the outsides it was just like y equals x squared. So with an even degree with a negative leading coefficient, we're thinking y equals negative x squared, which is a regular parabola that opens down. And we saw that when we made that fourth degree polynomial negative, okay, it just went upside down. It kind of looked like an M. Okay, so it had weird stuff happening in the middle, but on the outsides it looked like y equals negative x squared. Over here, odd degree. X to the first is an odd degree. Okay, and we know what the graph of y equals x looks like. That's a line with slope 1. And y equals negative x is a line with negative slope. Okay, so I'm not even going to write out as x approaches infinity, y approaches infinity, and as x approaches negative infinity, y approaches negative infinity, because I don't want y'all to memorize that. I would rather you just think y equals x squared and y equals x, even, odd. Okay, you determine if it's even or odd. Go back to these basic 4 examples. All right, so for these polynomials, we've got ourselves kind of over here, okay, y equals x to the third minus 4x squared minus 11x plus 3. So you go in and you look for the highest power of x you can find, and that would be right here, x to the third. And really it's 1x to the third. So it's degree 3, and the leading coefficient is 1. So that's 3 is an odd number, okay, so it's an odd degree polynomial. 1 is a positive number with a positive leading coefficient. So we're thinking y equals x. So we don't really know what's going to happen in the middle, but in general, it's going to kind of look like that. So as x is approaching infinity, as we're going to the right, the line is going up. So y is getting larger and larger and larger. So as x approaches infinity, y is approaching infinity. And then as x approaches negative infinity, okay, we're looking to the left. What's happening as we move left and left and left, the graph is going down and down and down. Y is approaching negative infinity. Right, we don't write that y is equal to infinity or negative infinity because infinity is not a real number and equals is only a relationship that two real numbers can have. Okay, over here, I've got negative 3x to the 6 is the largest power of x that I'm seeing. So I'm going to say that the degree is equal to 6. And the leading coefficient is negative 3. Okay, so that is an even degreed polynomial with a negative leading coefficient. Okay, so we're thinking y equals negative x squared. Okay, that looks like that. But maybe I should have actually drawn it like, okay, it's coming from below. I don't really know what's going to happen in the middle, and then, it's going to go down at the end. Okay, so as x approaches infinity, as we go to the right, it's going down. Y is approaching negative infinity. And as x approaches negative infinity, as we go to the left, it's also going down. So y is also going to approach negative infinity. And that's pretty much what we've got with this type of problem. And so, on the quiz next time, that'll probably be what it starts with. Tell me about the end behavior of the following polynomials. And I'll leave the other two for practice at the beginning of class next time. All right, next we're going to talk about turning points. The number of places where the direction of the graph changes, where it goes from going up to going down, or from going down to going up. And so I'm going to just kind of like write down a couple of them. Y equals x to the first looks like, like that. No turns. Y equals x to the 2. That's a parabola. Okay, it decreases and then it increases. It has one turn. Okay, y equals x to the third. Well, we can see that doesn't really have any turns. Remember, it got flat and then it kept increasing. But we do have that other one. This one. Okay, it has, here I see 2 turning points. Okay, so I'm going to kind of copy that. So what I'm saying is that degree 3, so something like x to the third minus x, I can just tell you that's going to have shape like that. That has 2 turns. But it could also have no turns. Okay, that's entirely possible as well. Like when we looked at that graph of y equals x to the third, it just was flat for a second. Okay, and then, let me think. We had one, it was, this is the one that looked like a W, and so, I mean, that might be a little sharp, but you get the point. And this had 3 turns, and so I think at this point you're seeing kind of a pattern. Bless you. So, what I'm saying is that it's not a guarantee. It's a guarantee that a first-degree polynomial has no turns and a second-degree polynomial will have exactly 1. But for a higher degree, if you see 2 turns, you know it's at least a degree 3. And if you see 3 turns, you know it's at least degree 4. So if you were to see 10 turns, which would be very hard for us to, cook up a graph that had that besides just hand drawing it. If you saw 10 turns, you know the degree is at least 11. Just in general, the degree is going to be at least 1 more than the number of turns. We'll have quite a bit more to say about that in a few minutes. So with knowledge about, the number of turns implying something about the degree and the end behavior, and we can tell whether something has an odd or an even degree, we should be able to match up these four graphs to these four equations. Okay. First off, I'm going to just talk about kind of the end behavior. Okay, I see both of these are the arms of this graph are going in the same direction, and this one as well. So what does that mean as far as the degree? Does that mean it's even or odd? So you think about y equals x and y equals x squared. Just always stick with those two. Does that look more like a parabola or like something that's going in two opposite directions? It looks more like a parabola. It's going both arms down, which means it's kind of like x squared in the sense that its degree is even. Okay. So for b and d, I can already say that that's not going to be 1 or 3. Okay. 1 and 3 have odd degree, so that's just not going to be able to be matched up with graph B or graph D. So I'll actually write that in. And then we'll look at the number of turning points. Okay. So let's start with this one. This one has 2 turning points, so the degree is at least 3. That doesn't really help us, right? Because it could be degree 5. And that's something I've got here, so I can't really tell if it's 1 or 3. So what I need to do is I need to think about the end behavior. Okay, so see that it's coming from above and then going down. All right, got distracted. The degree is at least 3. It's coming from above and going down, so it's kind of like y equals negative x, meaning that it needs to have a negative leading coefficient. So negative leading coefficient. So the only one that has a negative leading coefficient with degree at least 3 and odd is number 1. Okay, so I'm going to just say C. Meaning that over here, A is going to have to be number 3. Okay. Now we can see that there's 1, 2, 3, 4 turns, meaning the degree is at least 5 and it's odd. So I probably, I could have started with that and then deduced that C went with 1. But, 5th degree at least, positive leading coefficient because it's coming from below and going up like y equals x. And so I've got that. Okay, now for B and D, here I've got 1, 2, 3, 4, 5 turns. So the degree is at least 6. Oh, that means it has to be number 2. Right? It couldn't be negative x to the 4 because there's too many turning points. And then over here, you see we only have 1 turning point. So we know the degree is at least 2, and it's got to be even. So it's 2 or 4. But the interesting thing about this is that it is degree 4. So that just goes to show you that you can't just say 1 turning point, it has to be degree 2. It doesn't work like that. All right, now we're going to solve some equations, but that have degree 3 or higher. And the thing is that we know the quadratic formula that is the big gun we can pull out to solve any degree 2 polynomial, or degree 2 equation. There is a cubic equation. It's really unpleasant, and it's not the type of thing you could possibly memorize. And it turns out there's also a quartic equation, but it's like really, really long. And again, very cumbersome. We're not going to use it. What we're going to do instead is the only way we're going to solve degree 3 or higher is by factoring. Okay? I think that will be really useful for y'all to know. So the only way we're going to solve degree 3 or higher is by factoring. Factoring, right? 482, I don't remember your number, but you're going to solve by factoring, regardless. Okay, so the first one we've got, very straightforward. X minus 3 times x plus 1 times x minus 2 is equal to 0. Okay, it's already factored for us. How convenient. Okay, well, I know that if things are multiplied together and equaling 0, that's only happening because one of those things is 0. So if these three things multiply together to equal 0, then either x minus 3 is equal to 0, or maybe x plus 1 is equal to 0, Or maybe x minus 2 is equal to 0. And we know that that would happen when x is equal to 3, x is equal to -1, or x is equal to 2. And so those are our three solutions. And we'll get into this more, especially once we start talking about complex numbers. But a third degree equation is always going to have three solutions if you count complex solutions. Some of the ones we'll have today will not have as many as the degree. In fact, I think maybe one of the next couple will have that. But for now, or in general, you're thinking third degree, three solutions. Just like second degree, parabola, maybe two solutions. But maybe one and maybe none. Okay, here we've got another one. Okay, so this happens to be equal to 0 anytime any of these factors is 0. So that could be x equals 0, x equals -2 for that one, x equals +2 for this one. And over here, okay, I'm not really seeing, just off the top of my head, what kind of x is going to make that equal to 0. Something that if I squared it and multiplied it by 3, it would equal 4. But I'll just solve this one. And it's like, yeah, you could maybe try to factor to the difference of two squares. Probably not the best idea. Or you could, use the quadratic formula or b equals 0. Not a huge fan of that one either. I think we're just going to try to directly solve on this one. And I am not a huge fan of directly solving on degree 4 or higher for reasons I might explain later. But I'm just adding 4 to both sides. I'm going to divide by 3. Whoops, that's x equals 2. And then I'm going to take the square root of both sides. Okay, so the square root of 4/3, or maybe the negative square root of 4/3. And so I've got 1, 2, 3, 4, 5 solutions. And this is a 1, 2, 3, 4, 5th degree equation, so it's looking good. Next one we've got, also pre-factored for you. It's ready to go. And okay, so we know if these two things are multiplying together to equal 0, then either 2x plus 5 is equal to 0, or x squared minus 2x plus 5 is equal to 0. One or the other. So we'll figure it out. 2x plus 5 equals 0. That one looks easier to solve, so I'm going to solve for that first. Okay, 2x equals -5. X is equal to -5 divided by 2. That's a solution. Or on the other hand, we've got this one. And so, okay, I see a second degree thing. I'm going to try to factor it. Okay, two numbers that multiply to 5 and add to -2. It's, that's not going to happen. Not going to be possible. So when I can't factor, what do I do instead? Yes, I see dismay being expressed back there from 216. Yeah, I'm going to use quadratic formula, he says. Okay. And so we know that x is equal to -b plus or minus the square root of b squared minus 4ac is going to be -20. All divided by 2a. But now it's going to ask me to take the square root of -16, and you're like, oh, I remember doing this in algebra 2, but I know we don't have to do this yet in college algebra. Okay, so I say that that's not contributing a real solution, so I'm just going to kind of ignore that, because we're only interested in real solutions right now. I think next unit, maybe the unit after, at some point, we're going to be very interested in these solutions, but not yet. Okay, so this one just had the one real solution, despite being degree 3. Okay, now we're going to move on to some that are going to ask you to factor for yourself. And this one, well, it's probably good that we, get ourselves back into the thought process of factoring, and so we're going to, factorize this one, and two numbers that multiply to 6 and add to 5 are going to be 3 and 2. And then I trust that we know how to find the answers from them. All right, notice that this one is very similar, except it's degree 3. Basically what we did was we just bumped up the power by 1 on all of the terms. So what we're going to do is we're going to factor, just like we did before, except, we always got to remember when we're going to factor, is there a greatest common factor? And I see x in all of these things, at least 1 power. So what I'm going to do is I'm going to factor out this x. I'm going to be left with x squared, 5x, and 6. And then this thing here is still factorable. So I've got x times x plus 3 times x plus 2. And okay, that's going to happen to be when any of these three things are 0. So that could be when x is 0, or when x plus 3 equals 0, or when x plus 2 equals 0. So that one had 3 solutions. All right, next we've got a 4th degree polynomial, and we're interested in solving that. Okay, and just to add something to this, I'm going to scroll this down a little bit. And, if we had been faced with something like, negative 6x to the third plus 45x squared equals 3x to the fourth, we would need to set that equal to 0 in order to solve. Okay, I don't remember. I know I'm going to ask you to solve a couple of equations on the quiz next time, and I don't remember if they're set to 0. So if they're not, if we're going to factor, the idea is we're going to use the zero product property. And that is going to require that the thing be set equal to 0. All right, so over here I'm going to factor, and I think what is common to all of these things, I see at least 2 powers of x, and I think 3, 6, and 45 are all divisible by 3. And I see that the leading coefficient is negative. I don't like that. I prefer the leading coefficient to be positive. So what I'm going to do instead is I'm going to factor out a negative 3 and an x squared. And 3 times 15 is 45. And then this thing can be factored more. And then, okay, I say either negative 3x squared is equal to 0, and that's only going to happen when x is equal to 0. Maybe x plus 5 equals 0. Or maybe x minus 3 is equal to 0. So 4th degree, the 3 solutions. Really, we do have 4 solutions. It's that 0 would count twice if we were trying to get up to 4. And I'll have more to say about that in a few minutes. Here's one that's going to remind you about some other type of factoring pattern that we did in the first quarter, or maybe the second quarter, first semester. Okay, I've got x and 3 common, so I'm going to factor out the 3x, and I'm going to be left with an x squared minus 9. X squared minus 9 is factorable. It's a difference of 2 squares, so that's x plus 3 times x minus 3. And so I have, well, either 3x needs to equal 0, and 3x is equal to 0 only when x is equal to 0. I've got x plus 3 could be 0, so that would be x equals negative 3. Or I got x minus 3 could be 0, and that would be when x is positive 3. All right, so here I have x to the 4 minus x to the 2 minus 30 equals 0. And this is something that we didn't do in the first semester because we weren't dealing with things degree higher than 2. So I suspect that if we had written this differently and written it as maybe like, say, t squared minus t minus 30 equals 0, then you would have known how to factor this and solve. You would have said t minus 6 times t plus 5, and then t would either equal 6 or t would be negative 5. Hey, but that's not what we have. It's very similar because, in general, the pattern is this first power is twice the second power. Just like here, this first power is twice the second power. This is t to the 1. Okay, so what we're going to really do is say that this is the same, but where t is equal to x squared would kind of take us back over here. That's the idea, at least. So what we're going to say is that we can factor this thing in x squared. So x squared minus 6 times x squared plus 5 is equal to 0. Okay, so x squared minus 6 could equal 0, or maybe x squared plus 5 could equal 0. And this is going to happen when x squared equals 6, or when x squared equals negative 5. Okay. Well, we can solve this. We can say x squared equals 6 when x is equal to the square root of 6, or maybe when x is the negative square root of 6. If we squared that, we kind of lose the negative. Or over here, we're going to need to take the square root of negative 5. That's not a real number, so it's not going to contribute any real solutions, and we're not concerned with complex solutions yet, so we're just going to say those. That type of factoring, that's kind of new to us. You want to be able to recognize the pattern. And in fact, I might give y'all one to just to try factoring on your own. All right, this is one I want you to just to try to factor yourself. All right, we're not setting it equal to 0 or anything. We're just talking about the factoring process here. This is another one that kind of fits that pattern. You're going to need to factor this in u to the third, but I'm going to freeze it so that y'all can try it and see if you're doing it right. If you're working at home, pause the video, do this yourself, because the answer is about to pop up here in a few seconds. Okay, there you go. And so I factored it in u to the third. And you know, if you were unsure if you were doing this right, what you could do is you could check it by foiling. Because that's what factoring is. It's kind of unfoiling in this case. So u to the third times u to the third is u to the 6. Okay, that's 3u to the 3. 10u to the 3. And 30. Okay, so that's always, you know, kind of a good thing to think. Maybe you can kind of like mentally check and see, have I factored this thing right? Because that is maybe a factoring object we did not encounter in the first semester. All right, next we've got a degree 4 with 4 terms. So that's going to need to be, we're going to need to use group and factor because there's 4 terms. And we see that parallelism, 1 to -1, similar to -25 to +25. Okay, and then this is different from the item in your note packet. I switched it because I'm not going to be doing the one to the right of it until next time to practice before the quiz, and I just wanted to switch this one to be more like that one. Okay, so we're going to group and factor. So I'm going to take the first 2 things. I'm going to say what's common to both of these. Well, x to the third is common to both of these. Actually, hold on. I forgot to check for a greatest common factor. There is a greatest common factor here. So what I'm going to do is I'm going to first factor out an x. And then I'm going to group and factor. Okay, so I say there's an x to the 2 in common to both of these. X to the 2 multiplied by x minus 1. And then on the second one, I see this 25 in common to both. So, you know, I'm thinking maybe I would factor out a positive 25, right? And I'd be left with a negative x plus 1. But if you remember, the thing with group and factor is that we need this to be the same as that. So this isn't working. I'm going to have to kind of go back and factor out a negative 25. And then I'm left with a x and a negative 1. So then these are the same. And so then I factor out that x minus 1. Okay, I still have this x over here, and I'm still going to be left with an x squared minus 25. Now, this is still all equal to 0. And x squared minus 25 is x plus 5, x minus 5. And so then I can say that, well, if these 4 things multiply together to equal 0, one of them is going to have to equal 0. So x could be equal to 0. X could equal to 1. If x plus 5 was equal to 0, x would be negative 5. And if x minus 5 was 0, x would be positive 5. Now, a parenthesis bracket, no different. I just used the brackets to show that it was like kind of really draw the distinction between that and the parentheses. But if you're, I'm not very good at drawing different size parentheses, I think is really what it is. And so I want one to be bigger than the other, and so that's the best way I can do it. All right. Next, we're going to talk about basically what happens when you see the same factor more than once. Like if we had x squared plus 4x plus 4, that's x plus 2 times x plus 2. We see that twice. What's going to happen as far as our graph when that happens? Maybe you remember from Algebra 2 or Pre-Cal or something, or maybe you don't, and I'll show you. What we're going to do is we're going to make another one of those sign charts, except as opposed to when we did the fractions, you know, the rational functions, these are going to be pretty easy to handle. So I'm going to make myself a little number line. I'm going to split it off at 1, 3, and 5. And then I'm going to choose a representative from each subinterval. Okay, I'll choose 0, 2, bless you, and 4, and 6. Right? So at x equals 0, I plug in x equals 0. I get -1 times -3 times -5. Those are all negative. 3 negatives is going to make negative. X equals 2. Well, 2 minus 1 is a positive number, but 2 minus 3 and 2 minus 5 are both negative. Okay, so I've got a positive times 2 negatives. That's going to be positive. Okay, x equals 4. The first 2 will be positive because 4 minus 3 is 1. And then the last one will be negative. And then if you choose 6, or maybe I'll change this to like 100. Right? If you choose something bigger than 5, like really big, everything's going to be positive. And so that's going to be positive. Oh, and this one over here had 1 negative, so it's going to be negative. All right. And it's not in the instructions, but eventually we're going to want to graph these things. And so, thinking about how polynomials look, they're nice and smooth. These are going to be the zeros. I'm going to just draw a sketch of this. This is a third-degree polynomial because I see 3 factors, each with just 1 power of x in them. And it's going to have a positive leading coefficient, so it's going to come from below, like y equals x. It's going to go up. It's negative, positive, switches back to negative here, and then it's going to be positive. And that's a pretty good sketch of this function. And so I'm just going to sketch as I'm making these sign charts, because that's going to be something you're going to be asked to do next time. Okay, now we're going to do the same thing, except this x minus 1 is going to be squared. So we're going to see what happens, to the signs of the function when we add this repeated factor. Okay, so I'm going to go in, I'm going to make another number line, and I'll divide it at 1, 3, and 5 again. And I'm going to choose the same representatives. I'll choose 0, I'll choose 2, I'll choose 4, and I'll choose 100. Now the thing is, this factor on the left here that I'm underlining in green, it's always going to be positive, right? You take a negative number and you square it, it comes back positive. You take a positive number and you square it, and it comes back positive. The only thing that could be not positive is if we plugged in x equals 1. But we're not going to be plugging in x equals 1 because it's right there, right? That's not one of our test numbers. So this first factor is always going to be positive. So I'm just going to kind of preemptively fill in positive for all of these. All right. And then, okay, x equals 0. 0 minus 3, negative number. 0 minus 5, also a negative number. Okay, so two negatives, that's going to make positive. Okay, positive over here. X equals 2. Positive, 2 minus 3, negative number. 2 minus 5, also a negative number. So see how we didn't really have a change in any of the signs of the factors because of that squared thing. Going from 0 to 2, x minus 1 is the object that would change signs. But since we squared it, it didn't. So I'm still positive. Okay, at x equals 4, I've got positive, negative, positive. It's 4 minus 3 is 1, and that 1 is a positive number. And then 4 minus 5 is negative 1. So that's 1 negative, that's that number. And at x equals 100, everything's going to be positive. So when I go to make a graph of this thing, I know that it's going to be equal to 0 at 1, 3, and 5. I know it's 4th degree because I see, kind of 2 powers here, 1 power here, and 1 power there, so it's a total of 4. So it's 4th degree with positive leading coefficient, meaning it comes from above and it goes up. But you can even see that from the sign chart. Okay, it's positive, and it's going to go, but it goes from positive to positive, so I guess that means it's got to go like that. And then it's going to change sign here and go back up. Okay, so we call this a double root. We might say that it has multiplicity of 2. But regardless of what we call it, it's going to cause a bounce on the graph. And if you're interested in why that is, it's for a calculus reason. So, stay at it with the math classes, and eventually you'll find it. Okay, the last one I've got for y'all is got one with a triple root and one with a root with multiplicity 4. I suppose you could call that a quadruple root if you wanted, but that's not the type of terminology I've heard in the past. All right, so again, 1, 3, and 5. Should have just copied this number line onto the clipboard. I feel like I've written this a bunch of times. Okay, so at x equals 0, okay, I take negative 1 to the third power, and that's negative. I take negative 3 to the fourth power, and that's positive. I think that's always going to be positive if we take something to the fourth power. And 0 minus 5 is negative. Okay, negative, positive, negative. 2 negatives is going to make positive. X equals 2. 2 minus 1 is 1 to the third is a positive number. Negative 1 to the fourth is a positive number. And 2 minus 5 is negative 3. Okay? So notice that around this x minus 1 to the third, we did observe a sign change. Okay, so odd degree, or odd multiplicity, right? See, here we have this 1 here. It's going to change signs. Even I'm expecting it's not going to change signs at x equals 3. So I'm expecting when I plug in x equals 4 to get back something negative. So I've got x equals 4. I'm going to have 4 minus 1 is 3 to the third is positive 27. 4 minus 3 is 1 to the 4 is positive. And 4 minus 5 is a negative number. Okay, so we, again, same thing, because of that even multiplicity. And then when I plug in x equals 100, everything's going to be positive. And that will make that positive. Okay. Okay, so we know on kind of the last one, it's going to go up to infinity. We know this is 0, this is a 0, that's also a 0. So it's going to go up to infinity. And it changed, from negative to positive. Okay, here we know we didn't observe its sign change. It was negative, negative. Okay, now at x equals 1, because of the triple root, it's going to pass through hesitantly. If you look at it if you look at the graph of this, say you put it into a TI-84 or something, and actually graphed it, you would see. Oh, it won't let me zoom in that much, but you could see that the graph was going from smiling to frowning. And again, the reason why this is going to always happen in a triple root is kind of a calculus thing, but it will slide through hesitantly. Okay, I think there's some other terminology I've heard for it before, but I really like when they say it hesitates before it goes through. I think that's pretty indicative of what it's doing. And yeah, and then over at 3, it's bouncing because of the even multiplicity. I think if there's anything else I have to say about this. Oh, when you go to make a sketch, if it's third degree, or if it's a multiplicity 3 root, and you don't put it sliding through, but it's still changing signs, that's going to be okay. That's not going to be the end of the world. We can deal with that, because really we're looking for a general sketch, right? And we use these to solve the inequalities, so, if the sign changes, the sign changes. I'm not that concerned with how the sign changes. Does it do it confidently? Does it do it hesitantly? That doesn't really matter. So in conclusion on multiplicity of zeros, what I'll say is if the multiplicity is 1, then the graph is going to kind of pass through confidently. If it has even multiplicity, 2, 4, 8, 100. It's going to bounce at that root, corresponding root. Okay. And then if it has an odd multiplicity that's greater than 1 or greater than or equal to 3, oh, I forgot to write that this is bouncing. It's going to pass through hesitantly. And I do have to credit 803 from my calculus class who coined this terminology, confident and hesitant, when I was doing Algebra 2 a couple years ago. I do like that. I think that's all I got for you today. No, it's not. I'm going to call back to the very first page and draw your attention to a triple root that we saw sliding through hesitantly right at the very beginning of class. Y equals x to the third. That has a triple root at x equals 0. And so it's passing through the origin hesitantly.